Our final video for Unit 5 and the final video for this semester is about quadratic applications. So far we spent a month and a half on quadratics. We've gone all the way from just factoring them up to solving them and graphing them. Now we can finally do applications, which is just, again, a fancy way of saying doing word problems. I recall what the vertex of a quadratic is. It's either the highest or lowest point on the graph. All right, so if it's going down, it's the highest point. If it's going up, it's the lowest point. And when we're doing a lot of applications, we're going to be searching for a maximum or minimum value. Well, maximum just means you're at the highest point. Minimum just means you're at the lowest point. So really, whenever you see maximum or minimum in a word problem, it's really just asking you to find the vertex of the quadratic. So again, it's just a way of hiding something you already know how to do. It just takes you one extra step of realizing that's what you're supposed to do. All right, so ball is thrown into the air and its height is given by h of t. All right, I don't have to read the expression. This should be a t and not an x. It should be the same variable. What is the maximum height of the ball? All right, well, we're looking at a word problem that's asking us to find the maximum. We also recognize this is a quadratic equation. So if we have a quadratic and we're finding the maximum, that just means find the vertex. All right, so this is just finding the vertex of this expression of negative t squared plus 10t plus 45. All right, one thing you have to be careful with here, we haven't had to do it in any of our other examples because there's one extra step I didn't want you to have to do. To do completely squared, you have to have just a 1 in front of that squared term. Right now we have a negative 1, so what I'm going to do is factor out a negative from everything. Like that. And then I can do completing square on the thing that's in the parentheses, all right, because that's more normal. We normally just have a normal t squared. All right, so completing square, we divide that number by 2 to get negative 5. We square that number to get positive 25. All right, so now what we're going to have is the negative is just going to hang out there pretty much the whole problem. But now we know we have to add 25 to keep our perfect square. But then we also have to subtract 25 so we don't change what equation we're talking about. Again, that negative is going to hang out. That first 3 terms is going to turn into t minus 5 squared. And that last term, negative 45 minus 25, is going to be negative 70. And now we can distribute the negative into the 2 different pieces. All right, so our final answer is going to be negative t minus 5 squared plus 70. All right, so that's our vertex form for the quadratic. We have just that negative because you kind of one extra thing to worry about that we didn't have to do before. But now we know our vertex is at positive 5, positive 70. And what is the maximum height of the ball? Well, we're inputting time, so our x value here is the time, and the output is the height. So our maximum height is going to be 70. And there's no unit, so 70 feet, 70 meters, 70 miles, whatever it is. But that's our maximum height because that's where the vertex is. Our graph would look something like this. All right, and our vertex is there at the maximum height. All right, so again, the kind of shortcut thing is to remember if you see it's a quadratic equation and they're mentioning maximum or minimum, you're finding the vertex. All right, here we have the cost of a piece of artwork, and we're going to find the minimum price you would pay for the art. So again, recognizing that this is a quadratic because we have something squared, and they're asking for a minimum. Same thing, we're just trying to find the vertex of this quadratic. So we're going to start off with x squared plus 12x plus 30. We take our 12, we divide it by 2, we square it, we get 36. So now we have to add 36 to create our perfect square. But we also have to subtract 36 to make sure we don't change what function we're talking about. And then we can factor the first 3 terms. We combine the last 3 terms to negative 6. And then we see that our vertex is at negative 6, negative 6. And I guess I made a mistake because that doesn't really make sense for the problem for the price to be negative 6, but whatever, that's the answer. The minimum price you have to pay is them paying you $6, which doesn't make sense for the problem. I probably should have changed that equation a bit. All right, but still, when you're finding a minimum, it just means you're finding the vertex. So one more application I'll have to do. All right, the first one is pretty much just asking you to find the maximum or minimum, and that's the only new thing you have to know is that maximum or minimum means finding the vertex. So nothing really brand new, just kind of one extra step. All right, but this one actually will be a whole new process. All right, so one of these applications that gets used a lot with quadratics is maximizing the area of some rectangular space. All right, there'll be kind of two big steps you have to do. And it's kind of similar to stuff we did with systems really early on in the semester. All right, but it'll be a little bit different. So let's go through a problem and see what it looks like. All right, so a farmer's creating a rectangular garden using 100 feet of fencing. What is the maximum area they can enclose? First of all, let's kind of like explain the situation. They have 100 feet of fencing, so they could do a 1 foot wide rectangle, which would make the long part 49 feet. Because then they have to do a 49 on this side and a 1 on that side. So that'd be 100 feet of fencing, and the area of that rectangle is 49 times 1 is 49. They could also do like a 10 foot wide rectangle, and that would make this side 40. So that all adds up to 100, and that rectangle would have 400 square feet of area. All right, so you can see by changing the dimensions of the rectangle, I can change how much area I get. There's a big difference between having 49 square feet and 400 square feet. We want to know what is the maximum area they can enclose with some rectangle. All right, so again, we have any rectangle. And what's the maximum area in here? Well, the area of a rectangle is the length times the width, L and W. And we're going to maximize that, but right now we have these two different variables, L and W, so we need to figure out a way to turn that two variables into one variable. And this is something we did when we talked about systems before. But right now we don't have another equation, but we can create another equation because you know the fencing that goes around the outside of this rectangle, we have 100 feet of it, and it's going to get broken down into 4 parts. There's a W part at the top, an L part on the right. On the bottom, it's a rectangle, so it's another W part. On the left, it's a rectangle, so it's another L part. So that's 2W plus 2L. All right, and here's what we did back in systems. If we had these two equations, we could solve one equation for one of the variables and then plug it in. So what we're going to do is solve this perimeter equation, this blue equation, for either L or W. Let's just say, I don't know, let's say W, because the L's kind of look like 1, so we want to get rid of them. All right, so I'm going to subtract this 2L over. And I have to divide everything by 2. And know whatever the length is, the width is 50 minus that length. So we have this relationship now between the width and the length, and I can plug that in for W up there. I guess I should have solved for L, because now I'm going to solve L's. All right, but now I know W. Oops, let's use block again. All right, we solved that L, but W has to be 50 minus L. And now I only have one variable that I'm working with. And now this is the equation for area. And I want to maximize it. All right, and if I want to maximize something that is a quadratic, then I have to find the vertex. So now my final step is to find the vertex of negative L squared plus 50L. So now I have to go through the same steps again. That negative makes things a little bit more complicated. So the first thing we do is factor the negative out. L squared minus 50L. All right, now we can divide by 2. And then we square it. Negative 25 squared. I'm actually pulling out my calculator because I think I know what it is. I think it's 625, but I just want to double check. Yeah, I was right, 625, cool. All right, so that tells me in our equation, all right, again, the negative is going to hang out. L squared minus 50L. We have to add 625 to put it into a square. But then I also have to subtract 625 to make sure I don't change what my expression is. All right, the first three terms turn to L minus 25 squared. I just have a minus 625. And now I distribute that negative. So all that tells me my vertex is positive 25, 625. And if we think about what our x value is, our input going in is our L value. So that tells me my length should be 25. The thing I'm getting out is my area. So the maximum area I'm going to get is the y value there, 625. All right, so this is the process for finding these. We'll do a couple more examples. The basic idea is you make a perimeter equation. So step one is make your perimeter equation. All right, and then solve that for one of the variables. All right, once you have that solved, you're going to plug it into your area equation to get an area equation that only has one variable. And then after that, you're going to find the vertex. All right, so kind of break it down into those three steps. Solve your perimeter equation, plug it into your area equation, find the vertex. All right, so here are farmers creating 3 rectangular dog runs that will share sides. All right, if they're able to use 600 feet of fencing, what is the maximum total area? So this one looks a lot different, but it'll end up being pretty similar. All right, so if we have these 3 dog runs, all right, they're rectangles, and they're going to share sides, so they're going to look like this. Right? So we know our first step is to find the perimeter equation. And there's a bunch of different ways you can do this, but I want to find the maximum total area of this whole thing. So I'm going to call this whole side the width, and this side the length of the bigger rectangle. And what is my perimeter equal to? Well, first of all, I know there's 600 total feet of fencing to use. All right, so that's the total perimeter. And it's going to get broken up into, all right, let's see, there's a width there and a width there. So there's 2 width pieces of fence. There's a length here, here, here. And since it's all rectangles, all these are the same. There's 4 L's. And now that I have my perimeter, it's going to get broken up into 2 width pieces and 4 length pieces to create these 3 dog runs. I can solve this. I'm going to solve it for W for the only reason that when I divide by 2, it's easier than dividing by 4. So I'm going to subtract the 4L over, divide everything by 2. All right, so that's step 1 is creating my perimeter equation and solving it for one of the variables. All right, step 2 is taking my area equation. I know the area of a rectangle is length times width, but the width is 300 minus 2L. And then I want to distribute to make it look more natural. I'm going to get negative 2L squared plus 300L. All right, so that is my area equation. And then step 3 is to find the vertex of that quadratic. All right, so we have negative 2L squared plus 300L. All right, we actually haven't done this at all because it's kind of one extra step that I haven't wanted to make you do. All right, but again, we only do complete and square when there's just a 1 in front of that square term. So what I'm going to do first is factor out the negative 2. That's going to be L squared minus 150 L. I have to turn that into just a normal L squared first to make this pattern work. My B being negative 150, dividing it by 2 to get negative 75, and squaring it to get whatever the heck negative 75 squared is, which I'm going to check. 75 times 75, 5625. That tells me now that my equation, this negative 2 is just going to hang out. But now I know I have to add 5625 and then subtract 5625 to turn my equation into the first 3 turned into L minus 75 squared minus 5625. Now I distribute the -2 in. Oops, yeah. And 5625 times 2 is 11,250. All right, so one more step on completing the square than we've done before, factoring out this -2. But we still do all the same steps after that, distributing the -2 in, and we know our vertex now is positive 75, 11,250. And the answer that we actually want is the maximum area, which is the output, the y value, 11,250. These problems seem long, and I guess it is long. It took us like 5 minutes to do. But you can see there's kind of just 3 steps you always have to do. Create and solve your perimeter equation, plug it into the area equation, find the vertex. All right, so you can break it into those 3 steps when you're doing these maximizing total area problems. You'll be able to get there. All right, here's one for you to try on your own. All right, just a normal rectangular garden with 40 feet of fencing. And here's the solution broken into the 3 steps. So the first one is our red box, our perimeter equation, because it's just a normal rectangle. There's just 2 L's and 2 W's. All right, so in this case, I solved it for L for no specific reason. I would take that and plug it into our area equation and do a little bit of simplifying. So this is step 2 up here. This is our area equation with only one variable. And then our last step is finding the vertex of that area equation, because it is a quadratic. Again, that negative sign complicates things a little bit, so I just factor out the negative. And I'm really working with w squared minus 20w. So when you're completing the square there, I have to add 100 and subtract 100. In the end, I just have to remember this negative is going to go to both those pieces. So it goes to the perfect square, and it goes to that number to make it positive 100. And my final answer is the y value, because that's the area, is 100. So the most I can enclose is 100 square feet of area, when I'm using this 40 feet of fencing. All right, so the skill check is going to be 2 problems. Again, they take a little bit of work, especially the area ones. So there's going to be 2 problems. One will just be a maximum minimum problem, like the first half of the video. All right, just telling you to find the max or min. And the other one's going to be a maximizing area problem, like the problems that we just did.